Zahradnik from Prague.
Okay, my talk will be related to that of Roberto, but I will concentrate instead of bounds and probabilistic interpretation, I will concentrate more on the combinatorial aspects. I will show you a method of, you know that in the cluster expansion of this partition functions, you have huge cancellations. So you can treat this cancellation with the help of several techniques. There was a technique of reduction to trees and resummation over trees. I will show you another method which also use trees, you know, but these trees will appear under different names. They will be cycles of cycles of cycles, or closed path and things like this. There will be also trees, essentially. You know, the method is very old. The beginning of my talk will be based on things which you can find, for example, in big Scott Sokal paper in, it was 3, I do not remember, in GSP.
No.
Your paper with Scott, it was in GSP.
Combinatorial journal.
Yes, no, I mean,
it's in Journal of Statistical
Journal of
Physics
Statistical
because it's
Physics.
the only journal that would accept a paper that long. Mayer, I think, is around 1940, isn't it?
Wow, so
I do not remember. Okay, so the subject, the point of my interest is the polymer partition function, which is a summation over collection of objects which are polymers. I will consider only the hard repulsion case, that is, polymers will be some animals living in a lattice, and incompatibility of polymers would mean that their supports, so polymer is a support plus some information, and incompatibility would mean that the supports would intersect. There are, of course, other cases. You can treat a soft repulsion case. Most of the formulas would generalize, but they would not be so nice. So I will restrict myself on the hard repulsion case. So this is the polymer partition function. I will give you some examples where these are polymers, and this is the weight of the polymer, which is a complex number. Here I wrote a minus in order to minimize the number of minuses in the forthcoming computations. I think the best way is to write minus here. Then, of course, I will not speak about alternating signs of the expansion, but I will have exponential of the minus, and the rest will have positive coefficients. So that's the way I prefer. And second, there are examples where minus appears very natural. Why? Because look at some classical examples. Sorry. So a very trivial one, of course, even if you start with this, then this is nicer with minus than with pluses. And my basic example will be determinant of Laplacian. That is determinant of matrix, which is identity matrix minus something. And so imagine Laplacian matrix, or something close to it, which is, of course, take definition of determinants is sum over permutation. Permutations are decomposed into cycles, and you can write down the determinant of this matrix as off-diagonal terms. And determinant appears a polymer partition function, where the summation is over all collection of polymers, which are just cycles of the permutation. They are compatible if they do not intersect. And if you write down, look for the minuses, then you really recognize that formula is like that. Here is minus, and the weight of the cycle is the product of the matrix terms of edges corresponding of the edges in the cycle. So that's one reason why I like minus here. Another reason is that even in classical Ising model, where of course you have plus, because this weight is e to the minus energy of the contour. Even in this case, we have old reformulation by Kramer, Swanier, Onsager, which is based on very ingenious construction, you know, that you write minus as a fourth power of square root of I. And if you properly assign signs to angles like this, square root of I, square root of minus I. Square root means of minus I means this, and 1 to this, multiply by activity which is smaller than a critical one, then you can write the usual Ising model in its Peier's formulation, either in low temperature or in high temperature case, because there is a duality. You can write in such a way. Okay, so there are some reasons why to write minus here. Two examples of what I want to show you. I want to show you a method of expansion as a canonical one. This is just the definition of generalized exponential function. But then there are some resummation methods, and I will show you a method which will give as a byproduct two well-known formulas. The one is for the determinant. Determinant of a matrix is equal to exponential of the trace of its logarithm. Here it means this. Here you recognize the sum over closed paths. So I will show you that, or at least I will try to show you that this formula can be viewed as a special case of a cluster expansion. And similarly for Orzanger case, it looks similar, but you don't have cycles in a lattice. You have cycles in a dual lattice. That is, these are the vertices and bonds are just pairs like this. But otherwise, it looks similar. And of course, what is Orzanger solution is computation of this sum, which is also some of the traces by some Fourier methods. Okay, so these are basic examples. So let us go again to the general scheme. So we have partition function, overall collection of compatible polymers having weight like this, and now you write it in a standard way, which is just which recognizes this object. First, the most important step is to write it over ordered collections, right, factorials. Then express the compatibility in terms of compatibility coefficients, which are denoted by C. C is equal to 0 if these things are compatible, -1 if they are hard incompatible. Otherwise, this coefficient C is between 0 and -1. So this term is equal to 0 if collection is incompatible. It is equal to if it is equal to 1 if it is compatible. And then the standard way is to expand this parenthesis. Then you obtain the sum over graphs on the set of indices 1 to n. C of G is product of incompatibility coefficients of all the pairs contained in the graph. So if you have H in the graph, you look whether whether there is a bond in the graph, and if there is a bond, then you look whether the polymers are compatible. And then there is a simple exercise, which is just play with multinomial formula that this partition function, if written in such a way, sum over all ordered tuples of polymers, sum over all graphs of this type, quantities of this type, decompose the graph into components, and you get the theorem, simple basic theorem, which is simple observation, in fact, that this partition function is exponential of something which looks the same, like here, but the sum is not from 0, but from 1. And here is one important additional assumption, that these graphs are connected on the whole set of indices 1 to n. Okay, so this is the cluster expansion, and now the question is, this is enormously large sum, so you should understand structure, you understand very many cancellation, and you should organize the result in a way which could be useful. An important role in my method will be played by the following very elementary lemma. This is very simple lemma. This is kind of folklore. That if you sum quantities -1 to the length of the graph over all connected graphs on a set of m points, then the result is -1 to n-1 times n-1 factorial. And n-1 factorial is an important thing. It is a number of cycles on a set of m integers. Well, here is the proof. Proof is nice but simple. Proof is by establishing a recurrent formula that if I denote this quantity by S, then I obtain formula that S is the sum over all the compositions of this corresponding set, and with removed first point of all, and in each decomposition you take again this quantity S. Here is minus. The similar behaves the quantity number of cycles, and this is more tricky. Here also you need some consideration, because what you are doing, you have connected graph, you erase all the bonds going from the chief point to the one, then you have components, and then you are summing over all possible connections with your chief and the component. This is the play with 1 minus 1 to some power, number of bonds, -1. That is, you can replace the summation over all this subgraph by one single minus. So you see that the sum is equal to the sum over all the composition, and so on. So you see this recurrent structure in this formula. More interesting it is for permutation, because if you take number of cyclic permutation on a set with n points, then here is the cycle, this is the chief, and here is the list of the other people sitting at the table, and this is a permutation on a set with n-1 points. This is decomposed into cycles, and again we have the same structure as before. So this is the simple but nice combinatorial lemma. Okay. So how I will use it in my summation? Just some notation. So the partition function is written as exponential of minus terms, which maybe here is not minus, here is part, of terms I will call cluster the connection of incompatible polymers and one concrete connected graph. And weight of such an object is the product of weights of the polymers, factorial, and product of minuses over the graph. I will show that there are very many cancellations, and here will be a method how to describe the result of this resummation. For this will be useful to introduce another game with inclusion-exclusion. That is, here I will use very heavily the fact that my contours are incompatible if they supports intersect. So here are two contours, and these points are intersection, which is S. So they are two copies of the same set, which is the intersection. And I will write minus, because in such pair contributes to by one single minus if it is in the graph. I will write it in terms of a sum of bipartite graphs of this simple type, just connecting corresponding copies of points in any point. This seems to be arbitrary modification of the result, but it will be very useful. So this is a cluster which I will call quilted. That is single minuses in edges where the graph G sits will be replaced by a more complex structure, that is by some graphs, which I denote by ash. With this, and the effect will be the same. The sum will be unchanged, but it will look
You
more.
say again what h's you're summing over?
I sum over all non-empty edges.
All
edges.
non-empty.
Non-empty in case I have a bond in the graph. And now I will reorganize this sum. I will reorganize this sum, and for this I will need, as usually, some auxiliary ordering of the lattice. So now I am in some lattice. I have some countable set, and the polymers are living on this lattice. I have some auxiliary ordering on this lattice, and I will take the first point of this ordering, and I will reorganize this the sum over such objects in the following way. And then now will come the crucial observation. The crucial observation is that I will take the chief point and I will erase all bonds of this kind in all pairs in the chief point, T1. And now components which the cluster is decomposed into components. The components can have simple or duplicate structure. These are simple objects. Component is simple if it is a complicated cluster of polymers containing, this is the duplicate, containing the chief point T1 only once in some polymer, only once. This is a duplicate because here I have two polymers in this cluster containing both the point T1. But I can organize the summation, I can bracket these sums correspondingly in correspondence to this component. So for each component, for each collection of components given by erasing all the points, all the edges T1, T1, if in some components I have a situation like this, then there is a bond which can be used or not freely. That is, you have two terms which exactly cancel each other. So if you look a little bit more carefully about this, the summation over clusters containing components like this disappear. They are cancelled exactly. So what remains? What remains are objects which are simple. That is, they can be very complicated, but they contain only one polymer containing the chief point T1. So what remains in the summation is summation over object like this, where each object has this red point, which is the chief point. And you sum over something which is very complicated inside, and you sum over all connected graphs on the set, here the 5 points of this chief set. Now we use this simple lemma that summation over graphs, this green graphs connecting this point is the same as summation over cycles. That means that objects of this kind are replaced by objects of this kind, such blossoms, where you have table with a cycle, and then you have very complicated objects, but containing only one piece of this chief point. And then you, of course, iterate this construction, again analyze the structure of this component, and so on, and you obtain something which I call cactuses.
How do you go from connected to cycles?
Because summation over green object like this, here, I sum over all connected. They must be connected because
you're using the calculation you did about.
Yes, this lemma, that summation over all connected subgraphs of a complete graph on this set is the same as summation over cycles. That's crucial, absolutely. So I can replace this summation over graphs connecting this chief point by summation over all possible cyclic orderings of these sets. So instead of this picture, I have such a picture. And again, I analyze the structure of the components. So I get objects which I call cactuses, which are constructed recursively, and which have essentially the same, not essentially, they have the same sign.
Components are the things you get by erasing the green edges.
Then we take the second chief point, and again, I analyze the structure of the cluster with respect to the first point of the lattice. Then I have objects which are complicated, but contain the first point of the lattice only once. And
Things that you get by deleting the green.
yes, and I have, take the second point of the lattice, and I am doing the same. Okay, this still looks maybe complicated, but it is not so complicated, because if you look at some examples, like that with the determinant, then so here's the summarization. So that partition function is expressed as sum over cactuses, which I described. And now I want to persuade you that cactuses are nice things. Because, for example, in this computation of determinant has polymers which are cycles. So we have a cactus of cycles. And now we have simple representation that cactus of cycles is nothing else than closed path. Because if you have a closed path, then you can look for visits of the chief points, and you can represent this closed path as follows. Closed path starting at the chief point, traveling somewhere, returning, another closed path of this time, and so on, and so on. So you see that closed paths are cactuses of cycles. And similarly, with some more observation, you have it in Ising case. That is, cactuses you obtain are closed paths in the dual lattice. So this gives you a very nicely looking expansion. You see that this class, that's what I find nice on this method, that you really see that the structure of these terms. It's not terribly complicated, because in examples like this, it gives you something very natural. Okay. So maybe that's almost all what I want to say. Of course, this is kind of an alternative approach to something which is very well known. There is nothing new. This is just another way of looking at classical things. So what would be interesting for me would be find some more complicated situation where you could obtain something not the same, because there will be no cactus, it will be something more complicated, but at least something which could be in spirit comparable to what I showed you. So, to summarize, we had some new look on classical things. We could continue it for using model. Look at the structure of this expansion near critical point. Actually, of course, it's a difficult problem. What is the asymptotic? But at least you can ask this question. What is most interesting for me are models which are massive, small perturbation of massive Gaussians. Then you obtain something which looks as follows. Polymers are closed paths, where weight of the polymer is just the usual weight of the random walk. But there are some decorations. I write them as point, they could be more complicated. And these decorations have negative weight, that is of course essential. And this polymer model, and this is my favorite object, but unfortunately I did not finish it yet. So this is the polymer model which I like, which describes massless perturbation of Gaussian field. Models like rotators could be described with the help of it, if it would work. This is something I am analyzing now. But the model looks nice in a sense. Polymers are closed paths with decorations. Compatibility means that decorations of one polymer should not intersect path of the other polymer and vice versa. So these are the polymers. Of course, this is not the same kind of compatibility as before. So you don't get cactuses or cycles of cycles. You get something more complicated, but that's something which still should be analyzed. By the way, this very simple lemma, you know, I have it for complete subgraphs. Maybe some commentators would be able to generalize it for some other classes of graph. For me, it would be nice to have it for bipartite graph, for example. The simple formula, sum of -1 to the length of the graph over all subgraphs of graphs of a complete graph, that it is equals to the number of cycles or the rings. Okay, so that's more or less all what I wanted to say. Thank you.
Are these things loop erased walks?
Which
Oh, these things here, are you decomposing a cycle, a closed path into loop erased walks?
Well, there are some loops. They play a very important role because here you have a minus. So each loop like this is a minus perturbation, so they add the mass.
No, but I mean, there's some canonical way. You take this cycle which intersects itself many times, and there's a canonical way of decomposing it into.
Unfortunately, I do not know this canonical way. So
Well, you have a way.
But even he's not obtaining non-intersecting random walk after that. It's not self-avoiding after you erase the loops. It's still not.
Oh! You haven't erased all the loops.
Yeah. So these are
By the idea is that this object add mass because this is like 1 minus something multiplied by the number of visited points.
Oh, I see.
And then you have structures which where each point has where these 4 points are connected in some more complicated graph. This should be estimate sum over such object, but I am not finished
yet. You mentioned an application to integrable models in the very first slide. I think you
Which
mentioned-
models?
I think you, in the first slide, I think you had the word integrable models. Did you try to use this to, like to find what physicists call exact results?
I missed.
like on
You said,
Saga.
one of your keywords was integral.
Yes, what I showed was essentially on Saga solution because I showed that the partition function of Ising model can be written as exponential to minus sum over closed paths in this dual lattice. And this is the intermediate step in Oswager solution. The next step is to recognize this sum as a trace, a sum of traces of powers of some matrix, compute spectrum of this matrix 4x4, show and then use some Fourier analysis to obtain formula for free energy.
And at the combinatorial level, is this true for the Ising model on any planar graph G?
This I don't know. This I did not test. Unfortunately, I did not test. I even did not test hexagonal lattices and things like this.
Because it would be really nice. I mean, if you had a formula, I mean, this Onsager solution or this Katz-Ward-Budovichenko version of it is usually presented on a square lattice. But
it doesn't
there
work.
ought to be a formula for arbitrary planar graphs, and I'd like to know what it's
But
for.
even on
Surely,
square lattice, it doesn't
I should look at
work.
it.
Even on square lattice, it doesn't work really because if you have periodic boundary
No, free
conditions, you
boundary
have
conditions. Free boundary, planar.
then you cannot use your Fourier analysis.
No, but that's
Well, usually
there are two stages of the analysis that the physicists confuse.
But these two stages do not match.
No, but they should. The first stage is the Ising model on any planar graph should be written in terms of linear algebra, some Pfaffian or determinant or something. The second stage is how the hell do you evaluate this determinant of Fappian? And right,
This
that,
is for
that
your-
second stage
yeah.
doesn't match, and the physicists cheat.
If you want to write it in
But-
terms of this contours somehow, in the first stage, you know, the contours with the weight square root of I, then you somehow, if you want to do this with periodic boundary conditions,
I
then you
don't.
have the loops that are
I
going
don't.
down.
That's what I'm saying. I want to do the first stage on a planar graph only for now. And I want to know whether the Ising model on a planar graph G can be written as a sum over some kind of closed paths.
This
on a
should be-
dual
this
graph
should
G
be-
star.
this should be true.
That's what this is suggesting might
Yes.
be so. I've wondered what's the right form of this Cotsward type solution for general planar graphs G, and this might be the answer.
I did not test it, but I would expect that the answer would be yes.
The next stage would be to do it on a torus where you have to put extra weights for winding.
You have 4 different classes.
Exactly. Instead of getting one Fappian or one determinant, you get a sum of 4. Because that might solve an interesting.
I have to look at it.
problem.
I mean, with David Bridges, we were looking at something which was similar, where you have a gas. I mean, for instance, a gas of disjoint loops plus a self-avoiding walks, which avoids the loops, and you look at the 2-point function. So you sum over a configuration where the walk goes from x to y in the numerator, and you divide by just the loops, and you can express this as a sum over random walks, and the weight going from x to y, and the weight depends on the loop erasure procedure. But actually, it turns out to be actually a consequence of an old result by Vienno and people in combinatorics. But I don't know if we have been able so far to apply that in like integrable models.